Welcome back to Physics 151 Online. We're now going to look in a very detailed way at the microscopic properties of an ideal gas, and using some very simple assumptions, along with simple physics that we know from Newton's laws, we'll be able to come up with a microscopic understanding of the meaning of temperature. And that's what's significant about this subject. It was first developed in the middle of the 1800s and was a very powerful step toward what we think of as the atomic theory or the molecular theory of matter. So what we're going to do is look carefully at what happens to a single gas molecule bouncing around off the walls of a container. And for this discussion, we'll think of the container as just a cube that sits with one corner at the origin, and we have in a volume V there are n molecules. Each of them has mass little m and velocity v. And what we'd like to do is figure out an expression for the pressure that's created when all of the different gas molecules that are inside the container bounce off one of the walls. So in order to do that, we need to figure out in a certain amount of time how many of these gas molecules will actually collide with one of the walls. So we'll focus on the right-hand wall of this container, and if this molecule has velocity v, then there's an x component to that velocity vector. And so within a time delta t, the only molecules that will make a collision with the right-hand wall of the container will be those that are within a length vx delta t of that right-hand wall, because that's the distance that they will travel along the x direction in a time delta t. Okay, so but then we have to take into account the fact that some of the molecules that are within that volume are actually moving to the left. They have negative x components of velocity. On average, half of the molecules should have positive x components and half should have negative. So what we can write down is the number of those molecules that will make collisions with the right-hand wall in a time delta t. So here's how it works. We have 1/2 because only half of them will be moving with positive v sub x, and then we'll take the number of molecules divided by the volume, and what we have in parenthesis here is the volume of this region to the right of the plane that's indicated with the dotted lines, right? So n is the total number of particles. In parentheses, we have the volume on the right-hand side, and then that's expressed as a fraction of the total volume of the container. So of the n molecules, half of them, and then the ones that are within this volume right here on the right-hand side, will strike the right-hand wall of the container in a time delta t. So that's Vx delta t times A, because that's the volume of that region. So each molecule colliding with that right-hand wall will rebound, and we know they have to rebound elastically. Now, how do I know that that collision that those molecules make with the walls of the container are elastic? Well, if we have a container that's in thermal equilibrium with its surroundings, then those molecules that are inside the container, whenever they strike the wall, they're either going to keep the same kinetic energy or they'll lose kinetic energy. And if they were to lose kinetic energy over many, many different bounces, they would continue to lose energy and the pressure of the gas would spontaneously decrease. Well, in equilibrium, we know that that doesn't happen. So as long as the system is one that maintains equilibrium, we can infer that those collisions the molecules make, at least on average, will be elastic collisions. So for a single molecule, we can now write down the change in momentum along the x direction. And I'll put the subscript 1 on here because it refers to just a single molecule. Note here that p in this context means momentum. In just a few moments, we'll be writing p down to mean pressure, but when we do that, it won't have an x or a y or a z component. So hopefully you'll be able to keep this straight. So the change in momentum is the final momentum minus the initial momentum after the collision. So the final momentum is to the left, so it would be negative mvx. The initial momentum is to the right, which is mvx, and the difference between those is negative 2mvx. Now, for the entire number of molecules that strike the wall in the time delta t, we can write down the total change in momentum of all the molecules along the x direction. That's pretty easy. We take the amount that the momentum changes for a single molecule, which we now know is negative 2 mvx, and multiply by the quantity from the previous slide, which is the total number of molecules that's striking the right-hand wall of the container. And when we simplify, we get this expression here. So n, again, remember, is the total number of molecules, v is the total volume of the container, and then we have the familiar quantities here where the a represents the area of one of the container walls. Now, from the change in momentum, if we remember Newton's second law, we can now calculate the force exerted on these molecules when they collide with the right-hand wall of the container. In the x direction, then, the force is the change in momentum along the x direction divided by the change in time. So all that does is it cancels out the factor delta t in this expression. Now, F sub x is the force exerted on the molecules, and since the pressure is the force exerted on the container by the molecules, then we can take the opposite of this quantity to get the net force on the walls of the container. That's F sub wall. And pressure, since we remember that pressure is defined as force per unit area, then this expression, and I'll just go back one slide here so you can see it, this expression here, F sub x, we're going to divide by a and take the opposite of it, and so we will get the result n over v times mv squared vx right here. All right, so now we have the pressure on the right hand wall, and if we were to do the calculation along the y direction or the z direction, we'd get the same answer. So the pressure is the same no matter which wall that we're talking about. Now, this is a little bit inaccurate simply because we know that not all of the gas molecules will have a single well-defined value of v sub x. Some of them will be moving more along the y direction, some more along the z direction, and some more along the x direction. So what we really should write down in order to have an accurate expression is the average value of the square of the velocity along the x direction. So we'll put parentheses around that and just indicate that what we really want is the average. But that's kind of an awkward expression. So we would much rather try to write it down in terms of the average of the square of the speeds for the gas molecules. And we can do that because there's no reason to think that the x and the y and the z directions should be any different from one another. If we are ignoring the influence of gravity, which would be very, very small on the molecules, then the x, y, and z directions should be the same. If we take our cubic box and rotate it 90 degrees to exchange the axes, the properties of the gas shouldn't change at all. So on average, we should expect the squares of the x, y, and z components of velocity to be the same. And if that's true, then the overall average in the square of the speed, which is just the sum of these three terms, would simply be 3 times one of those terms, as long as all three of them are equal to each other. So what this allows me to do is solve for Vx squared average and replace that in the equation above for the pressure. What does that give me? Well, Vx squared average then becomes 1/3 of the average of the square of the speeds of the gas molecules, and then that allows me to write down the pressure now in terms of the average of the square of the speeds and not in terms of any one component. Excuse me. So we see that the answer that we got from the previous slide is this. And this should look familiar because what we remember about the ideal gas law is it tells us something about the product of the pressure and the volume of a gas in a container. So on the right hand side of that expression was NKT, where capital N is the number of molecules. Of course, we can write this as little n times r times t, and they mean the same thing, but because the expression that I have above already has the capital N in it, I'll write the ideal gas law in this form. And of course you see that capital N cancels out. So what we can solve for, if we solve for the square of the velocity, the average of the squares of the speeds, we get 3 Boltzmann's constant times the temperature over the mass. And if we take the square root of both sides, we get something that's called the root mean square velocity of gas molecules in an ideal gas. So it's called the root mean square because it's the square root of the average or the mean of the squares of the velocities. So here is a nice relationship that allows us to see that the velocity of these molecules, at least on average, depends on their temperature as well as their mass. So how fast is this? Let's just take a moment to do an estimate for a gas whose properties we know at a temperature that's around room temperature. So molecular oxygen, O2, which is about 21% of the air that we breathe. Room temperature is around 300 Kelvin, and in the formula for this root mean square velocity, we need to know the mass of the oxygen molecule. Well, oxygen has 2 oxygen atoms because it's a diatomic molecule, so twice the mass of a single oxygen atom in the molar form is 2 times 16 times 10 to the minus 3 kilograms per mole. We divide by Avogadro's number, and what we get is the mass of a single oxygen molecule, so kilograms per molecule, which is pretty small. Plugging that along with the temperature and Boltzmann's constant into this expression gives us an answer when we take the square root of about 480 meters per second. So gas molecules that are whizzing around inside the room where you are right now are moving at several hundred meters per second. And of course, that will depend on the temperature, but also on the mass. So if we have hydrogen gas around, along with oxygen gas, we would expect the hydrogen molecules to be moving quite a bit faster because they have a smaller mass. All right, well, let's finish off this discussion by going back to the expression for the mean of the squares of the velocities of gas molecules. And what we're going to do is use that to calculate the average kinetic energy of these molecules. So we just use 1/2 mv squared, but now we're using the average of the v squared. And if we plug that in here, we get 3/2 Boltzmann's constant times the temperature. And that's for a single gas molecule. So what about if we have our entire sample of n gas molecules? Then this translational kinetic energy, which you can think of as the kinetic energy of the center of mass of all the molecules, is 3/2 the number of molecules times kT, and we can replace the number of molecules times Boltzmann's constant with the number of moles times the gas constant, just like we did previously. So this gives a nice simple expression, and it also tells us what the microscopic meaning of temperature is. So apart from the constant R and this factor of 3/2, what temperature really represents is a measure of molecular kinetic energies. And so very soon, coming up, we will use this equation to calculate the internal energy of a collection of gas molecules, and we'll also show how to include the influence of rotational and vibrational energies that molecules have when it's more than a single atom. So oxygen or water or CO2, those are molecules that are made up of more than one atom, and so in addition to translational energy, they can also have rotational and vibrational energies. Now, one last thing, and this was one of the really amazing results that James Maxwell discovered in working out this kinetic theory of gases. He was able not just to find out an expression like we have done for the average speed of gas molecules at a particular temperature. He was able to calculate the entire distribution, and he was able to show that there is a function f, which is a function of the molecular speed, which tells us the probability of having a gas molecule at a particular value of the speed. And he was able to show that there's a constant out in front, which depends on the mass as well as Boltzmann's constant and the temperature, but then it had this exponential term. It had a v squared, but then also a decaying exponential term that caused there to be an exponential tail in the distribution. at high values of velocity. And so here's my schematic attempt to show what this function looks like. You can see that for low values of the velocity, where this exponential term is roughly equal to 1, the function rises rapidly proportional to v squared. So it goes up in almost a parabolic fashion. But then what happens as v increases, this exponential term kicks in, and of course since it's e to the negative quantity, and that exponent depends on v, as v increases, this exponential term gets smaller and smaller. So the function rises but then reaches a peak value at some intermediate value of the speed, and then finally as v gets larger and larger, the exponential term dominates and it decays away back toward the value of 0. So this Maxwell-Boltzmann distribution function is very important in understanding the properties of all of the gas molecules. And what we showed in the previous slide was the average value of the square of these velocities, and you can also calculate, if you find the value of v that corresponds to the peak in this function, you can also find the most probable velocity for gas molecules at a particular temperature. And you'll have some practice doing that on a homework assignment. So this has been a whirlwind introduction to the kinetic theory of gases, but hopefully gives you some flavor for the power of this very simple model of gases consisting of spheres bouncing around inside of a container, and it helps us to understand the properties of those gases. It shows us where the ideal gas law comes from at the microscopic level, and it also gives us a pretty nice explanation of the meaning of temperature at the molecular level. I'll see you in class.